look at the day number that's on here. Isn't that an interesting number? 28.
What?
Topic 2, stoichiometry. Wow. Actually, I was debating over the summer whether to make a video over this or to wait and teach you guys oxidation reduction the correct way. And so I decided to wait until this semester to present redox equations for acidic and basic solutions. I hope that you guys talked about oxidation in general chem, but who knows. First thing I want to talk about is oxidation numbers. Does anybody remember what an oxidation number is or what it represents? No. An oxidation number is a potential charge that an element may have when it's with another atom. Again, an oxidation number is a potential charge that an atom or an element may have when it's with another element. In other words, if I have an element all by itself, what should the charge on that be? This is my smart class, I can see that. If an element's all by itself. In other words, let me give you an example. What's that?
Positive charge.
Positive charge? Wow.
Negative charge.
Negative charge? Let's say we just have copper all by itself. What's the charge on that? No charge. Again, unless it's with something else, it won't be excited or charged. Okay? So Richie, this is you. When you're by yourself, nothing should be happening. You should be not excited and neutral, right?
Just laying face down.
That's right. It's not until some non-metal comes along and says, I need something. In other words, what's the charge on iodate? -1. Good, that's one of our 10 polyatomics. So we have 2 of those, and so the copper now has what charge? +2, because if this has a -2 charge, because there's 2 of those, then the copper has to have a +2. Okay. Now, how did I know what those charges are? Well, in general chem, I did it a very basic way. In other words, I lined them all up and found out how many of each I had. And again, this isn't the only way. This is just the way I taught it in general chem. How many coppers do I have in this compound? And we're doing the first example here. 1, good. How many iodines are in this compound? 2. How many oxygens? 6. Now, the nice thing is, oxygen will always have a -2 charge. So, we know that all of the charges on oxygen equal -12. What's the whole charge on this compound? In other words, what's the charge up here? That's 0, so it's neutral. If I had a -1 there, then the whole charge on the compound could be -1. We haven't spoke about that yet. We'll talk about it a little bit later on. So for right now, that value should be 0. All right, we just said that copper had what charge again?
Positive.
Why?
Because 2 is a -2.
Good, because each iodate has a -1 charge, and there's 2 of those, and since we have 1 copper, it has to have a +2 charge. All right, so now what we have, we want to find out what the charge on the iodine is. If the iodine were all by itself, in other words, it's the only non-metal, what would the charge on the iodine be in this case? In other words, look at your periodic table.
5.
If it were just copper and iodine, what group is it in? -1, good, because it's 1 away from the noble gas. However, since it's with oxygen, it has a different charge other than -1. So what value should be here for everything to equal 0?
10.
+10. And since there are 2 of those, we'll divide that by 2. And these are your oxidation numbers. Okay? Not these. These are just your charges that all the atoms exhibit. These are your oxidation values. Okay? And again, there's other ways of doing this. This is just the way that I show it. All right, looking at the next one, letter B. You have Mn3, PO4, and then 4 of those. So again, finding out what the manganese, the phosphorus, and the oxygen are. Those are my 3 elements that I have in here. Let's see, how many manganese are in this compound? How many manganese?
3.
3. How many phosphorus?
4.
4. How many oxygen?
Yes, he says.
What?
16.
Ah.
Crazy.
And, well, we know the charge on oxygen will be -2. So all those are -32. And the charge on the whole thing is 0. What's the charge on the manganese? Charge on manganese. Well, it's a transition metal, so it's not magnesium, which is +2. How can we find out what the charge on the manganese is? Is it possible to use your polyatomic?
Yes.
Yeah, I would. So we know phosphate's a -3, and we have 4 of those, and we have 3 manganese. So what must the charge on the, what must the charge on the manganese be?
+1. +3.
4. Good.
Never mind.
Okay. And then when I add all these up, what value should be here for that to equal 0?
20.
20. Very good. And then 20 divided by 4 is
5.
+5. And that's your oxidation numbers. Okay. Try the last one on your own. Don't peek up here. What is that? H2SO4. What is that called? Anybody remember the name of that?
Sulfuric acid.
There you go.
Hydrogen something?
Not hydrogen something, but sulfuric acid. So what should the sulfur be? What'd you get, Leanne? 6? And there's only 1, so it has to be 6. Good. Okay. Easy stuff, right? Specify which of the following are oxidation reduction reactions and identify the oxidizing agent and reducing agent, the substance being reduced and the substance being oxidized. Actually, let's change the instructions because College Board said that we don't have to know the agents anymore. So cross off oxidizing agent and reducing agent. We just need to know who's oxidized and who's reduced. I don't think it's that big of an issue that we don't know the agents, but definitely we need to know who's oxidized and who's reduced. Also, probably the best way to figure this out is to write down the charges. So I'm going to write the equation down. So we have SiCl4 plus 2Mg makes 2MgCl2 and Si. And this may or may not be balanced, doesn't matter. Let's go ahead and determine the charges on each of these. Let's skip the silicon. What's the charge on each chlorine? Why?
Charge.
The why?
That didn't explain it.
What did he say?
He said why.
Said why?
Oh.
Why is it?
Because it's 1 left from the...
Good. It's a negative. It's in group 7A. Good. So it's a halogen. So what must the charge on the silicon be?
4.
4, because there's only 1 of those, so plus 4. What's the charge on magnesium here?
2.
Plus 2?
Yes.
Richie, what's the charge on magnesium here?
2.
2?
Positive 2.
Positive 2?
Yes.
Who's magnesium with?
No one.
No one. Okay, now think of it like this. If it's magnesium or 2 magnesiums, so we consider it the twin, are you going to get excited around your twin?
No.
Hopefully not. Okay, good. So, no. But what's the charge on magnesium here?
Positive 2.
There we go. Chlorine, -1, because we have 2 of them. And silicon, 0. Good. So when we look at this, let's first of all look at the chlorine. What's the charge on chlorine here? Each one? -1, -1. Is that gaining or losing or changing charges? No. So when we look at who's being oxidized and reduced, I've got a thing on the sheet that says Leo, says Ger. Anybody have that in General Chem? Okay. Leo means lose electrons, and you're oxidized. It's hard to write this way. Okay? So losing electrons, you're oxidized. So if the GER is gaining or gaining electrons, is reduced. Okay? So losing electrons, you're oxidized, gaining electrons, you're reduced. So you're either gaining or losing. If the charge doesn't change from one side to the other for an element, it's not being oxidized or reduced. It remains the same. So we don't have to worry about that taking place. Silicon has what charge here?
4.
+4. Over here it's a
0.
0. And this is a half reaction for the silicon. And I don't know if you guys did this in General Chem. If you did, that's great. If not, you'll learn it today. So silicon has a +4 charge and it goes to a no charge. So did this silicon +4 have, I'm sorry, did it gain or lose electrons to get to 0? Gain?
Yes.
Good. In other words, we gain electrons. In other words, no charge over here. This is a +4. Technically, this is becoming more negative, right? Even though it's not negative, it's becoming more negative. It goes from +4 to 0. So the only way it can do that is -4 + 4 = 0. So if we see electrons on the left side or the reactant side, the silicon +4, is it being oxidized or reduced?
Reduced.
It's reduced. Good. Okay. And looking at the magnesium, goes from 0 to +2. So 0 +2. The magnesium, did it gain or lose electrons when it went from here to here?
Lost.
Lost. And how many did it lose? 2. Very good. So in this case, since it's losing electrons, in other words, we had all the electrons here. In other words, magnesium, I think, has 12. Is that element number 12? What number is it? 12. Okay, so it has 12 protons and 12 electrons. Here, it still has the same number of protons, but it lost 2 electrons. Okay. All right. So in this case, the magnesium, or the neutral magnesium, is oxidized. Okay. And then when you put these two together, red and ox, you got redox. So we have we do have a redox equation here. That was actually the first question asked. So the silicon +4 is reduced. The magnesium with no charge is oxidized. So go to the next. Here in B, I took out anything that didn't change. Okay, so we have copper with no charge, and I'll put the 0 there. 2 silvers +1, and it goes to 2 silvers, no charge, and copper +2. Okay? So you've already got your charges on there. Copper goes from 0 to +2. So is copper being oxidized or reduced? See how good you guys are.
Re-oxidized.
Oxidized? Why?
Because it loses electrons.
You know, where are the electrons at? Over here?
Okay.
Yes.
No. Remember, electrons are negatively charged, so we want to make sure the charges add up. So +2 - 2 = 0. So the copper is being oxidized, and the silver, I'll just do one of them, just a no charge. So what side is the electron on for this one? Left side or right side? Over here? Yes. As a heads up, the electrons better be on opposite sides for each half reaction. This is an oxidation half reaction. This is a reduction half reaction. Can you have more than 2 half reactions in a chemical equation?
No.
No? Why?
Because they're halves. Just 2.
There you go. You can only have 2 halves. Very nice. So this is reduced. So if something's being oxidized, something must be reduced. Okay, if something's going to give away electrons, something has to pick them up. It just can't throw them out into space. So is this a redox equation?
Yeah.
Yeah. Good. If we have something that's oxidized or reduced. Good. All right. C, I think we're on. right, letter C. HCl plus some ammonia makes some ammonium chloride. Nice. All right, let's go ahead and write the charges down. What's the charge on hydrogen here? +1. Chlorine, -1. Charge on nitrogen here. Now again, if it's listed first, it acts like a metal, right? +3. And the hydrogens are negative in this case. Whoa. Hydrogen can be positive, negative, or neutral. Yeah. Chlorine over here is a -1 charge. Let me draw the Lewis structure for this. This is going to make some of you very happy. All right. Now, 3 of those hydrogens were negatively charged. Well, 3 of them are still negatively charged. This nitrogen still has its +3 charge, and the hydrogen that we had over here has a +1 charge. I'd write this down if you haven't seen that before. Ammonium's pretty weird. It has 3 hydrogens that have a -1 charge. The central atom, which is nitrogen, has a +3, and the other hydrogen that it got from the HCl is a positive charge. So have the charges changed from the reactant side to the product side? The charges changed. Grace, have they changed? No? What do you think, Richie?
What was the question?
Have the charges changed from the reactant side to the product side?
Yes.
You say yes? Christian, who's right, Grace or Richie?
Richard.
Wrong.
You failed
This
me
is
again.
not a redox,
What?
since the charges don't change. In other words, that hydrogen, +1, +1. Chlorine, -1, -1. Nitrogen, +3, +3. Each of these hydrogens is -1. These are all -1. Charges don't change, not redox.
Dang it.
What? What? What's the matter,
I was
Richie?
just admiring your brilliance.
What? What?
So it's not a redox equation. So there's nothing being oxidized and there's nothing being reduced. All right. Also, write this down somewhere. I don't know, you might see it somewhere in the homework. I don't know, like 1H somewhere. I don't know. Just somewhere. I'm sure it might show up. I don't know why I think that or say the back side. This is why I waited. Wasn't the front side. The front side you guys did in general chem. No problem. Easy piece of cake. This is the fun stuff. Okay? And there's actually 4 steps today when we do our acidic redox equations. In other words, these are taking place in an acidic solution. Tomorrow is it tomorrow? Do we meet tomorrow? Thursday, we'll talk about it in a basic solution. And there is 5 steps. Today it's only 4, so I'm being gentle. All right, well, let's write down what we know first of all, and then I'll go over the steps here. So we got copper plus NO3. Mix a little copper plus 2, some NO.
No.
Yes.
That means there's no.
Yes. All right. Anytime I'm giving you a problem like this, I promise it'll be a redox. So something's going to change. I'm not going to give you that much space to work these out and not have something take place. So don't write not redox and move on. All right. Actually, let's pick the easy one. In other words, going from copper no charge to copper plus 2. We'll have 2 half reactions. And though there won't always be an easy one, but when you get an easy one, you want to take it. All right. Now, the copper, no charge here going to copper plus 2. Is that copper oxidized or reduced?
Oxidized.
Oxidized. So where do I put the electrons? Over here?
On the
No.
right, on the right, yes.
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 Don't hit
Okay.
me.
So the copper is being oxidized, which means that something else is being reduced. Well, we don't really care. We're not identifying who's oxidized or reduced, but we do have these two eliminated. So now we can look at the nitrate going to NO. All right. So now what we get to do is we want to go through the 4 steps since we have some oxygen in here. The first step is let's make sure that we balance the non-oxygen, non-hydrogen elements first. So the non-oxygen, non-hydrogen would be nitrogen in this case. Do I have the same number of nitrogens on both sides?
Yeah.
Yes.
Check. Good. All right. Next thing we want to do is balance the number of hydrogens. And by doing that, if we need more oxygen, then we will add water. Okay? Again, this is an acidic solution, so we have a whole bunch of water molecules and a whole bunch of hydrogen ions since it's an acidic solution. So how many oxygens do I have on the left?
3,
How many on the right?
1,
So how many water molecules should I add to balance the oxygens?
2 on the right.
2. Very good. Okay. So my nitrogens are balanced and my oxygens are now balanced. But now I need to balance out the hydrogen. So if I need hydrogen, I need to add hydrogen ions. Again, this is an acidic solution, so it's not hydrogen gas. So how many hydrogens do I have on the right? 4, so I need to add 4 hydrogen ions. Okay. All right. Now the last thing is I have to balance out charges. So charges to be balanced. Okay. And by doing that, we need to add electrons. Okay. So electrons are what charge? Positive or negative? It's kind of a dumb question, but it's a good one. Electrons are what charge? Negative. So we are adding negative charges. So this side has no charge. What's the charge over here? Total charge on the left side for this half reaction. How many? How many positive charges do I have? 4. How many negative charges? 1. So it's a +3 over here, right? So I got +3 and no charge. So if I need to add electrons, which side will I add the electrons so that the charges are the same on both sides? Doesn't mean they need to be 0. They just need to be the same. Left, how many? 3. Good. Okay, so now I have, in this case, both sides have no charge. All right. So now we've got everything balanced. We've got the non-oxygen, non-hydrogens balanced. We've got the oxygens balanced. We've got the hydrogens balanced. We've got the charges balanced. Awesome. Now we're ready to add all these guys up. Now, how many chemical equations have you seen? And again, I skipped a lot of this because this was stuff that we should have taken place back in day 26. And since, or 28, sorry, and since then we've worked out a lot of chemical equations, equilibrium and whatnot. How many equations have you seen electrons in the balanced equation? 0, and you're not going to start today. So we want to make sure that we have the same number of electrons on both sides. So if I have 3 down here and 2 here, what do I need to do to get rid of those? Multiply the top by 3 and the bottom by 2. So electrons are gone. Okay? You're not going to see electrons in your final equation. All right, now, is there anything else that can be eliminated or reduced? Doesn't look like it. And I'm talking about on each side of the equation. So there's no other hydrogens over here, and there's no other waters on the left. So whatever's left, we bring everything down. Now, the key here is keep it on the respective side of the arrow. The plus sign just means and. So if you want to start off with your hydrogens first and then add your copper and then the nitrate over here, I don't care. Whatever you want to write. But just make sure you have the correct numbers. And the correct charges. So if copper has no charge, don't put a charge on there. Then we have 8 hydrogen ions here, because again, my multiplier, 2 times the 8, and then the 3, of course, for the copper. 2 nitrates. And I think we've got everything on the left. So now on the right, the 3 times the copper plus 2. And then we have 2 NOs. how many waters do we have on the bottom? 4, right? Okay. Now, let's check charges first of all. If charges are the same on both sides, you're probably about 95% correct. All right, so we've got no charge on the copper, 8 times a +1, plus 2 times a -1. So a total charge of +6 on the left side, and then 3 times +2 and 0. So we've got +6 on this side. Charges are the same. That's a good start. Then let's check number of atoms. I've got 3 copper, 3 copper. 8 hydrogen, 4 times 2 is 8 hydrogen. 2 nitrogen, 2 nitrogen, and then 2 times 3 is 6 oxygen. 2 times 1 plus 4 times 1. Good. There's your balanced redox equation. Now, the second sheet that I gave you is this problem laid out. It may not be an exact same process, but it has those steps somewhere involved in there. All right, we have lead, and then some lead oxide, sprinkled in with a little sulfuric acid, and it produces one thing, lead sulfate. Isn't that cool? So 3 things make one. Ah, crud. Now, if you see a problem like this and it bothers you because you're like, wow, there's 3 things on the left, there's only 1 thing on the right, go ahead and find out what the charges are. What's the charge on the lead here? And you don't have to do this. You don't have to. But what's the charge on the lead here?
0.
0. Good. Charge on the lead here?
4.
4?
2.
2?
The EB is 2 plus 2 and O.
2?
No, 4 plus
4. Yeah, you're right the first time, Richie. Come on, have some confidence.
If he
you
asks a
that
question, just stick with it.
And what's the charge on the lead here? 2?
Yes.
Yes.
Good.
Woo.
The sulfate's -2. Very good. So based on this, it looks like lead's being oxidized and reduced. Is that possible? Yeah, I said I wouldn't give you a problem if you couldn't do it. All right, so doesn't matter. I'll start with this one, this lead. And, well, it only has 1 product. It's lead sulfate. All right. Do we have the same number of non-oxygen, non-hydrogens on both sides? Non-oxygen, non-hydrogens.
No.
No? Why?
Because we don't have a sulfate on the left.
Good, we don't have sulfur on the left. The leads are good, but we don't have any sulfur. So how do we get sulfur?
Sulfur.
Use what you got, okay? So it's a package deal. You can't just say, sulfur, come on over. No. If you're marrying sulfur, you got to get all the kids too, so they all come over. So to get the sulfur, you got to get it all. All right, so now we have the same number of lead and the same number of sulfurs on both sides. Okay? So let's now balance the oxygen, and let's go in that order, because if you try to balance the hydrogen then the oxygen, it's not going to be pretty. So oxygens, are the oxygens okay?
Yeah.
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 Okay. And then hydrogen, we got 2 over here, right? So we need to add
H2O.
2 H's, not a H2O. Don't add any water. We've got our oxygens are golden. Okay? Charges on the left. What's the charge on the left here? 0. Over here?
2.
Plus or minus?
Plus.
Plus, good. So we need to add 2 electrons, right? Okay. All right. So that looks good. So let's do the other one. Lead oxide going to lead sulfate. So is it possible to use the same thing over again?
Yeah.
Yeah, okay. Because these aren't balanced. So don't freak out and go, well, I've already used that once. That's okay. You can use it again if you need to. Don't worry, it'll reduce that if we use it more than once. All right, so do we have the same number of leads and sulfurs on both sides? No. So how do we get sulfur?
Add
And
H2SO4.
H2SO4.
Add the sulfuric acid again. It's a package deal. All right, so now I have the same number of lead, same number of sulfur. Do I have the same number of oxygen?
No.
No, I have 6 over here where I only have 4, so I need to add
H2O.
2 waters. Okay. Hydrogen. Do I need to add any hydrogen on either side? No?
No.
No? Yes?
Yes.
How many?
So
2. Very good. Because I have 4 hydrogen over here, only 2 over here. Alrighty. What's my total charge on the product side for this half reaction? 0. 0 plus 0. And over here we have
Plus 2.
plus 2, so I need to add how many electrons?
2 electrons.
Good. Now what's bad is you have the same number of electrons on both sides, so there's no multiplier, but we do want to cancel or eliminate the like terms. Is there anything else I can reduce or eliminate? Good. Nice, Lauren. Good. So the hydrogens are gone. Anything else? No. Everything else has got to come down. All right. So also do realize this. These are arrows. Treat them like an equal sign. So since these are on the same side, we don't subtract them or reduce them. We actually add them together. So we have 2 H2SO4s, 1 PB, 1 PbO2, and then we have 2 lead sulfates and 2 waters. Okay. Charges. What are the charges on each side? 0. So the charges are good. Now let's just double check atoms. 2 times 2 is 4 hydrogen. 2 times 2, there's 4. 2 sulfur. 2 sulfur. We have 2 times 4 plus 2, which is 10 oxygen. 2 times 4 plus 2, good. And then 2 lead, 2 lead. Awesome.
Awesome. Awesome.
All right. And hopefully you're starting with what?
Zinc.
Good. Unless you just like doing the hard stuff first, that's fine.
Stop.
What do I need to add to the right side? What's that? How many? 4? 1? 4? 2? God, this is a terrible auction. 4! All right. And so now we have, there's 3 hydrogen, and we have a total of, was that 11? So how many hydrogen on the left? 8? Alrighty. Looks like there's no charge on the right side for this half reaction, but there's a,
8 on the left.
so we need how many electrons?
8.
Oh boy. So charges are balanced, atoms are balanced. Looks like we need to multiply the top by 4. By electrons. Yes.
Oh, okay.
We must. And I don't think there's anything else that can cancel or reduce or anything. So bring down whatever's left. And are the charges the same on both sides?
Yes.
Yeah, +8 on both sides. 8 times +1, 4 times a +2. All right, take a look at your homework on the back side. I'll let you pick one, either B, C, or D. Those are the ones to pick from. All right, and it makes H3ASO4. And some might think, well, that's just what we did. Ooh, not even close. Oh boy. Shh. Please. All right. Which one do you want to start with?
Nitric.
Okay, that's a good call. Doesn't matter. Seriously, it doesn't matter which one you start with. So the non-oxygen, non-hydrogens, are they balanced?
Yes.
Yeah. So how can I balance the oxygens?
Add H2O.
How many?
2.
2. Over here. And then what do I add? 2 each? How many? 4. Very good.
Right, 4.
All right. Total charge on the right side is 0. On the left side we have a +3. So if this is 0, if I add electrons over here, it's going to make a negative. So I need to add electrons on this side. How many?
3.
Good. Okay, and again, they just need to be the same. They don't have to be 0. All right, so that half reaction's done. Looks good. AS2O3 going to H3ASO4. All right. Are my non-oxygen, non-hydrogens balanced?
Yes.
No.
No.
No. So what do I need to do?
We need to add AS to the right.
I need to add a what?
An AS on the right side.
AS? How do I do that?
By adding another H3ASO4.
Put a coefficient in front. Okay. So technically I am adding another one of these, but just do a coefficient there. Okay?
Okay. Right.
Because we need to have 2 arsenic on each side. Okay. All right, so now oxygens. How many oxygens do we have on the right?
8.
8. And how many do we have on the left?
3.
So we need to add
5 H2O.
5? Yeah, that's okay. Okay. How many hydrogens do we have on the left?
2.
Left, your other left.
On the left,
10. How many hydrogens over here?
6.
6. Good. So I need to add 4 hydrogen.
We can do this.
You do this. You do. All right. On the left side of this half reaction, no charge. On the right side, we have a +4. So we need to add
4 electrons.
electrons. Good. And we have 3 electrons here, 4 down there.
Multiply both.
That by 4, that by 3. All right. Now, is there anything that we can reduce or eliminate?
H2O.
Okay. How many H2Os do we have on top? Total?
8.
8. Okay, so let's put an 8 there. How many do we have on the bottom?
15.
15. So these are all gone, right? And this goes from 8 to what?
7.
7. 7 waters. Okay. So we'll get rid of that. Anything else? It can be H plus, good. How many hydrogens do we have up on top? 16. How many over here? 12. Okay. So these are all gone, and these go to 4. Okay. Any others? I think that's it. And then everybody else will bring down. and be careful when doing this. So we've got 4 NO3s, and 3 of these AS2O3. I think that's everything on the left. There's my arrow. On the right side, we have 4 NOs. And is that 6?
Mm-hmm.
H3ASO4. Okay. Now, box that in. See it? All right. Let's check charges first. What's the total charge on the right side? 0. Good. On the left side, we have +4, -4, which is looking good so far. Now we just need to check atoms. All right, 7 times 2 is 14, plus 4 more is 8, so that's, what, 18? 6 times 3, 18, good. 7 times 1 plus 4 times 3 is 12, 19 plus 3 times 3 is 9, so 28. And then we have 4 plus 6 times, yep, 28.
Solid.
4, 4, 6, 6. Awesome.
Awesome.
Fantastic.
You're going to wish you had a marker board to work these things out. That's why you want to be super neat on these. But really important, make sure you remember these, the order. What I didn't put on here is the first step, make sure that we balance the non-oxygen, non-hydrogens first. Okay. So if it's a non-oxygen, non-hydrogen, then we use the coefficient. If you needed more hydrogen, okay, we wouldn't add a coefficient in front of that. We'd actually add hydrogen ions, okay, for an example. All right. Iodine, that's a -1 charge, plus ClO with a -1. What is that called? ClO with a -1. What is ClO with the -1? Chloride, yeah, very nice. Hypochlorite, good. I3 -1 plus a Cl -1. So they've all got -1s. Wonderful. Which one do you want to start with? Neither?
Iodine.
Iodine? Okay. So we'll go with I -1 to I3 -1. Okay. Are we good? No. Go ahead.
Same amount of iodines on each side.
So what do I do?
So you add 2 iodines to the left.
Do that?
That'll work.
That will work.
I like that.
Okay, so my iodines are balanced, and I don't have any hydrogen, I don't have any oxygen, so don't worry about trying to get creative in doing that. So then the last one is balanced charges. So what's my charge on the left side? Very nice. Okay, so 2 electrons. So you have to be careful that this whole thing has a -1 charge, and that this has a -3. That has a -3 charge. Okay, because there's 3 iodines with a -1 charge. All right, then the ClO -1, going to just Cl. All right, so the non-oxygen, non-hydrogens elements, are those balanced? Yeah, chlorine. So how do I balance the oxygen?
H2 is the right.
Put a water over here. Then what? 2 hydrogen ions, good. Then, uh-oh. How do I make the charges the same? 2 what?
So 2 electrons on the left.
2 electrons on the left?
It's the same.
Is that what you said,
One
Ron?
electron on the left.
What is it?
Wait.
It's the same. Oh, no, it's not.
You need 3 to get to the -1 on the
Yeah.
right and -1 on the left. Oh.
You need 2.
Yeah, 2. To the left.
Good. 2 electrons. In other words, the total charge beforehand is a +1 and a -1. So to get it the same, I need to add 2 negative charges. Or even better, these guys will eliminate. So now you got -1, -1 again. Again, it needs to be the same charge, not 0 charge. Oh man, these have the same number of electrons. I know. Is there anything else? No. Who picked this one? This one stinks. You definitely want to watch the video for the other one, because it's a lot more involved. Maybe I can talk the other class into doing B. It's probably fine. Debbie tried, but... Alright, well, let's check and make sure we get the same number. I mean, these innocent ones can get us in trouble. So let's see here. What's the charge? Whoa, what is the charge on the left side? -2?
No, -1. No, 0, yeah. No.
I hate this because you keep having the subscripts and...
You have to look at that. So +2, -1, -3 more. So Debbie was good. -2. What's the total charge on the right side?
It's just -1. That's nothing to do with it. No, it's not. Negative.
This whole thing is -1.
And then
So it's -2. You guys are going to love Redox. 2 hydrogens on both sides, yes. 1 chlorine on each side, yes. 1 oxygen on each side, and 3 iodines. Nice.
D.
Look over here.
-1. And don't worry about the state, whether it's aqueous, liquid, or they don't care. Ooh, we've got a positive one here. What's that mean? Not much. All right, which one do you want to start with?
BR.
It's a good call. Okay. So BR -1 goes to BR2.
So then BR2 would be 0, if I was right.
Let's go in order. Okay, so do we have our non-oxygen, non-hydrogen atoms balanced?
Yes.
No.
Let's kid.
We have 1 here, 2 there.
No one else.
I got you.
Okay, so now we have our bromines balanced. And again, sometimes it's just as easy as seeing that. Sometimes there's a lot of other things with it, so be careful. All right, since there's no oxygen or hydrogen, don't fret with it, and don't get creative and start throwing water in there. All right, so we'll go right to the 4th step, balancing charges. How do we balance the charge?
Wouldn't you just add 1 electron to the right side?
Just 1 electron?
Yeah,
Is it 2 or 1?
When you add these,
Is it 2 or is it 1?
Add to the left.
Nick, quit talking, you're confusing me, alright?
All right, how many bromine -1s do we have?
1, 2.
2.
Hey, hold up.
So therefore, we need how many electrons?
2.
Good.
Hey, Craig, tell me why we don't have to...
Why is it on that side?
How come there's not a step there?
We want to balance charges, right? If I put 2 electrons over here, what will my charge for the whole thing be?
4. Yeah, I was going to say 4.
Wait, what would it be?
It'd be -4. -2 plus a -2.
Alright, Craig, tell me this. Why are we not messing with
I don't care what people say about you.
We will. We're just doing that half reaction first.
Okay, alright,
Yeah.
I was confused. Alright.
All right, so now we're done with that half reaction. And is that an oxidation or reduction?
That is I don't care.
It's an oxidation.
Oxidation.
It really doesn't matter, does it?
No, but it does if you find out that you have electrons on the same side for both half reactions. Then you got to really go back and say, where did I screw up?
Well, I'm not going to screw up, so.
Well, I always screw up, so...
All right. Do I have the same number of non-hydrogen, non-oxygen?
Water is not in here.
Yes, so the manganese are balanced. So oxygen,
We need
No, we have to add...
water.
4 water,
4 water.
4 waters on the right side.
We need 4 manganese.
okay?
Now we need H's.
We need H's.
So we need 8 H's on the left side.
So 8 hydrogen ions on the left.
So to get oxygen, you always have to add.
Hydrogen ion.
So
Yeah.
then we
Don't
got-
put H2 in. Because again, this is an acidic solution.
Okay.
Then we got to balance charges.
All right, yeah, let's do charges. So total charge on the right side is,
+2.
and again, I'm only looking at this bottom half reaction. What's the total charge here?
6, 8, 7. It's 7.
Plus or minus?
7.
Minus?
No.
Good. Okay. So we need these two charges to be the same.
So we need to subtract.
We're not subtracting
We need to
anything.
Add 5 electrons to the left.
5 electrons on the left.
Yeah.
Why could you not subtract?
We can't reduce anything or remove anything. We've got to
Why
add.
can't you
And
add
that
5
is a-
positive electrons to the right?
A reduction. That's a reduction.
So now the charges are the same on both sides.
There you go.
Okay?
Yeah.
Protons stay in the atom. The electrons get to change. They get to dance. All right, so now we have our half reactions are balanced. So now, what do we need to do?
Cancel them out.
Times the top one by 5 and the bottom one by 2.
Good. So top by 5, multiply the bottom by 2. Actually, I'll put
Wait, how do you decide to do that?
I looked at my electrons.
Oh, okay.
Since I have 5 of them here and 2 of them there,
Oh, you want to get.
I need 10 electrons on both sides for this problem.
Cross.
Okay. Looks like that's all we can reduce or eliminate.
Alright.
Might need a calculator for this one.
So we-
All right, so again, make sure that things are on the respective side of the arrow. So 5 times 2 bromines is
We'll go
10.
back to that one.
Oh, correct.
Bromines with a -1. We have 2 times 8, which is 16 hydrogen.
Oh, that's what it is. Oh,
Then we have 2 manganates,
man.
MnO4 with a -1. And I believe that's everything on the left. Okay, on the right, we have 5 Br2s, no charge. We have 2 Mn manganates with a +2. And we also have how many waters?
8.
8.
Greg, can I go the rest of them?
No.
Please?
All right, let's check charges. Okay. So -10 plus 16 is +6. -2 is plus what?
4.
0 plus a 2 times a +2 plus 0 is
4. Wait, where's the plus?
Those were golden.
Oh,
Don't have-
the 8. All right.
and then we have to check the number of atoms on both sides. We have 10 bromines. 5 times 2 is 10 bromines.
Yep.
16 hydrogen.
Yep.
8 times 2 is 16.
Where'd you
Good.
get the other +2 for the right side?
The right side?
Yeah.
Right there. 2 times the +2.
Oh, all right.
2 manganese.
Yep.
There's 2 times 1 manganese, which is 2. And then oxygen, we have 2 times 4, which is 8 times 1.
We did good. We did good, guys.
Goodbye.